Those are the two ways to operate it. And then there were these blocking models we talked about, if you remember. And the blocking models were so-called intermediate blocking. There were various terms for them. And it's louder, sorry, that's softer, good. There were various terms: intermediate blocking, complete blocking, right, cake filtration. And basically what that's telling you is, gives you some idea of what sort of fouling is occurring. Is the foulant adsorbing on the walls of the pores? Is it blocking the pores completely or partially blocking? And that's about where we stopped yesterday, right? So we will continue from that point as soon as they're ready. Are they ready? Okay, so we'll continue then from that point. And is there anyone online, by the way, today or not? Okay, so if they have questions or he or she has questions, let me know, okay? All right, so where were we up to? Let's see. So I summarized all this, and I think so this was our purification train that we talked about, and oh, let me try and, actually, Noel did this well for me. You can get a pointer, right? Hang on. Pointer options, laser pointer, got it. Okay, so we're talking about somewhere here, just before we start the purification. This is the bioreactor harvesting or clarification. Let me just briefly summarize this. So I think there are a few people who are chemical engineers or engineers, and the rest are life scientists. But in engineering terms, we like to talk about, transport equations, right? And actually, there are many transport equations. There's Ohm's law. There are many things. But all of them talk about a flux. And I thought I didn't stress this enough. The term flux is important. You can see here the flux J is the flow rate divided by the area. So this is a volumetric flux. You can have a mass flux. You can have many sorts of fluxes, right? But the flux is whatever is being transported divided by the area by time. So if it's per time, that's obvious. That gives you a rate, right? But the reason we divide by area is then we can compare different membranes. So with membrane A, B, C, which is better? It's hard to say. If you just did flow rate and the surface area was different, how can you compare them? So it's per area. So that's why we talk about flux. So in terms of mathematics, flux is 1 divided by A, dV dt, the derivative of volume with time. And it's written as 1 divided by A multiplied by this term here, where in the case of pressure-driven flows, delta P is our driving force, okay? And then Rm and Rc are resistance terms, because if you didn't have a resistance, right, you wouldn't need a driving force. You know, if you think of motion of particles, if you push a particle along here, it will keep going forever if there's no resistance, right? So there's a resistance to flow. And we break up the resistance in this analysis into two terms, a so-called membrane resistance and a cake resistance. So membrane resistance is the resistance for the unfouled, the clean membrane. So if you run water through this, that would be the Rm value you get. And mu is just the viscosity. It's a proportionality factor. But what it does tell you is that as your fluid becomes more viscous, the resistance increases, right? Which makes sense. But that's important in protein purification, because as you get higher protein concentrations, resistance does go up because viscosity goes up. And Rc is a cake resistance, and that increases with the amount of material that you process, because the assumption is there's particulate matter in this that's being captured, okay? So that's what I tried to summarize yesterday. Based on that, we can come up with equations. This is something called the Hagman-Polzol equation for laminar flow. It enables you to calculate the membrane resistance, okay? That's all. What is important in all this analysis is these are idealized conditions. This is actually quite important in industry, because what happens in industry, in biotech companies, is typically non-engineers are working and designing things. I'm not saying that's a bad thing, but the point is, if you don't know how these equations come about, you start applying them to situations that are not appropriate. And that's when scale-up becomes difficult, because suddenly they don't hold very well. So what's very important to remember in this analysis is you're talking about cylindrical, straight-through pores. They're not tortuous pores. So yesterday, I think Professor Jacob talked about track-etched membranes. They are a good approximation for this. But track-etched membranes actually are seldom used in the biotech industry. Anybody know why? Anybody work with track-etched membranes? Yes? You can use them, yeah. But you know why in the biotech industry they're not used? Couple of limitations. The porosity is very low. You cannot get high porosity track-etched membranes because the aim is you're firing particles that make holes. If you put too many, you won't get uniform pores. They'll be interacting with each other. So porosity is low, typically less than 10%. And that's not very helpful because you want high flux membranes. There's another reason that's interesting. This may be idealized and agree with what's here, but see, if you have a straight through pore, I mentioned yesterday, if you block it with the part at the start, the pore is blocked forever. If you have lateral connections, you can still make use of it right from the sides, and so it leads to higher capacity. So that's why track-etched membranes are not really used in this case, okay? So standard blocking, this is important, assumes that the solute adsorbs onto the pore walls. So the solute must be smaller than the pores, much smaller, for it to go and adsorb on the pore walls, but it slowly causes constriction of the pores, okay? Complete and intermediate blocking. So complete blocking is if the solute comes and we can use this one, right? Somehow. Is that right? I think. Am I right? Actually, I can, yeah. So complete blocking is if you have a, where can I write here? Okay. So if you have a pore like this, right? The part, and the pore is going down like this, the particle comes and completely blocks it. All right? And intermediate blocking is if it only blocks a fraction of it. That's the difference between those two. So that's the difference between these two. So it depends on the size of the particle. And you can see, therefore, that that's why I mentioned yesterday that one of the problems with this method is that actually the type of blocking can change as you keep running the process. Okay, this next equation, don't worry about it if you're mathematically inclined. It's just showing you how you can actually derive all of these blocking models from that Darcy's law and Hagen-Poiseuille equation, okay? And then this last table is important because this gives you, this actually solves it for you. It gives you linearized forms for constant pressure and constant flux. So if you are running an experiment, right, run a data infiltration experiment, you will get data. What sort of data will you get? If you run at constant pressure, you will get what? Flux, changes in flux with time, okay? And these then tell you how you should plot that. So you should plot, if you think it's pore blockage, you can plot Q divided by Q naught, right? The flow rate divided by the initial flow rate versus time on a log linear plot. And if it's a straight line, you get your value of beta. And if beta matches one of these, you're correct, okay? But the problem is you have to know what beta is before, otherwise you're going to do 4 different plots to try and figure this out. So a simpler way is to plot this expression here. So you have to plot the second derivative of time with respect to volume versus the first derivative, okay? And you do this on a log linear scale so that then beta becomes the slope, okay? So I think most of you would know what to do there. But all I want to point out is that to do this, you have to take experimental data. You have volumes collected as a function of time, but you have to differentiate them numerically, or so you take the difference in volume for a certain length of time. But the problem is small errors get multiplied, and you're taking a second derivative. So typically your data doesn't fit on a nice straight line. And as I said, the problem then is if you don't get one of these numbers, 2, 1.51, or 0, what do you say? Should I round up to the nearest number? Or do I say that it's just experimental error, so I round up, but I may be rounding the wrong way? Or is it because my fundamental assumptions are not correct? You see, and there's a lot of literature about this, which if you're interested, you could read. But that is one of the problems here. So these models are used a lot by people in industry, and we'll talk about them when we talk about virus filtration, to design virus filters. Millipore sells them based on what they call Vmax and so forth, which is coming from this. But the problem is that these may not apply, and so you may not get a good scale up, you see. So that's my whole point here. But this is typically what people do. And deviations from these actual values are often due to lateral porosity. So because when a pore is blocked, like in this case here, it actually, oh, it's gone now, sorry. It actually doesn't necessarily block the whole pore because you can get flow from the side coming in, okay? All right, so I've talked about these limitations, and that's about where we got up to yesterday. So what I main point here is the importance of lateral permeability, as it's called, so the flow from the sides. Okay, that's very important, and the importance of asymmetric membranes as opposed to track-etched membranes. So this brings us up to an interesting point, so-called symmetric and asymmetric membranes. So a symmetric membrane, as the name suggests, is one that if I look at it from the top or the bottom, it looks the same. It's symmetrical. An asymmetric membrane, if you look at one side, it will have a smaller pore size compared to the other side. Okay? So why do we want to design asymmetric membranes? And the reason is this. If you think of a membrane, so you want your membrane to, no, I'm going to do this again, I think. So you want your membrane to basically, here's your membrane, right? Like this, and it's got pores like this, and it's got lateral pores and all sorts of things like that, right? Now, if you think of it, you want this membrane to have a certain pore size, so you have rejection properties. You also want to minimize the resistance to flow. So if you have a very small pore size, take a nanofiltration membrane because you work in water treatment, or reverse osmosis. You want very tight separation, okay? But now if that, but you also, this has got to be mechanically stable. If it's too thin, it's going to collapse. Right? Now, if you have that thin layer all the way through, you have a very high resistance. So typically, you take your barrier layer and you support it on a much more open structure, right? That's just a support structure. So you come up with an asymmetric membrane, okay? It's not uniform throughout the whole thing. And typically, the way these are run, certainly in reverse osmosis, is that you have the barrier layer facing the feed, right? So the barrier layer is upstream and the permeate is coming through here. That is not always the case in bioseparations, which I will talk about now as we continue. So, so that's the idea of asymmetric and symmetric membranes. Okay, so let's move on. So membrane processes, microfiltration, pore sizes are 0.05 to 10 micron, retain cells, cell debris, we've talked about that. Generally run in dead end mode, I've talked about that. We haven't talked about sterile filtration yet. We have disposable units. I told you dead end filters, depth filters typically. One-time use, and you throw them away, okay? Tangential flow microfiltering is also used for bioreactor harvesting. I'm coming on to that in a few minutes. And virus filtration we'll probably talk about tomorrow, which is between microfiltration and ultrafiltration. Actually, think of virus filtration as taking a very, very well-formed ultrafiltration membrane barrier layer and supporting it on a microfiltration membrane, okay? That's roughly speaking what a virus filtration membrane is. Also, always disposable units. And then ultrafiltration itself is used for protein concentration and buffer exchange. Okay, so removal of cells and cell debris throughout the filtration media versus surface screening in microfiltration. So in a depth filter, you're using the whole medium. In microfiltration, like tangential flow microfiltration, even dead-end microfiltration, it's only the top surface. That is the barrier layer, okay? So the advantage is you have higher capacity if you have a depth filter. Clarification is used for monoclonal antibody solutions. Think of them as proteins. Removal of particulates and contaminants from acidified protein solutions prior to chromatographic processing. That's another application of depth filtration. Remember, I told you that aggregates are a major problem in the whole purification train. They're a problem because I don't know how many of you have run typical resin-based chromatography columns, but any particulate matter there is a big problem because it blocks the passages between the pores and it leads to pressure drops, and you can imagine if you're working at large scale, that's a tremendous problem. So removal of aggregates is important. Also, in your final drug formulation, you don't want aggregates, okay? So what else? Removal of particulates and contaminants is important. Depth filters used in conjunction with sterile filters to increase capacity of the sterile filter, and particle removal mechanisms are physical capture in narrow pores, multi-layer structures with graded pore sizes. We talked about that yesterday, more open pores going to more narrow pores, and then positively charged depth filters provide good removal of DNA, viruses, endotoxins. I think I highlighted that yesterday, that these depth filters are quite complex. They have hydrophobic components, they have charge-based components, so that they're removing different sort of contaminants as well as just by size exclusion removing cells. And that's important because if you can, so think of it this way, in the biotech industry, really the three main contaminants are viruses, host cell protein, host cell DNA, and then endotoxins and other things. But if you can remove some of those in the bioreactor harvesting or clarification step, you reduce the load on the subsequent purification steps, and you may be able to get rid of one of them, okay? So that's what people are trying to do these days. Okay, so depth filters typically are made of cellulose or polypropylene fibers with a filter aid. We've talked about that, diatomaceous earth, perlite, or activated carbon. Charged filters contain charged polymers, so you can have ion exchange as well. Multi-layer depth filters can have unique pore sizes that change as you go through the filter. 47 90mm discs inserted in plastic stainless steel housings is one way to design these. They contain air vents to prevent air entrapment and ensure complete utilization of the membrane. Trapping air is not a good thing. You want to always make sure there's no air trapped. One is because you will then get areas of the filter that's not being used. But the other thing is that proteins are often destabilized by air-liquid interfaces. And so you'll get more damage, more aggregation, you lose some of your product. Okay, so typically you don't want air trapped in this whole process. All right. The other thing is that the air around us is full of microorganisms. And so you can get contamination that way as well. Industrial scale utilizes stainless steel housings, 12 inches or 6-inch diameter, and these are some of the areas. And these are some examples of these filters. Okay. Now, cellulose depth filter media pads used for clarification, downstream of centrifuge, tangential flow microfiltration system. So I mentioned yesterday that we can have combined operations. You'd have centrifugation, but typically the downside of centrifugation is you need a second step, because what you want to do is get your liquid stream from the bioreactor harvesting step and run it straight into your capture step, which is typically a bind elute chromatography. It's a resin-based chromatography step. Anything left, particulate matter, will foul that particular column, you see. So typically, centrifugation by itself won't work. You will need an additional step. Depth filters could be used for that. They could also be used in conjunction with tangential flow microfiltration. I'll talk about that in a minute. But as I said, now we're trying to make standalone depth filters. Combination of fibrillated cellulose and filter aids combine to provide high capacity for challenging feed streams that include, as I said, cell debris, DNA, protein aggregates, and colloidal material. They often contain positively charged ligands that contribute to clearance of negatively charged species. Importance of electrostatic interactions are tested by running feed with increasing conductivity, particle size, zeta potential, provide information on removal mechanisms. So here's another important point. The buffer you use in bioseparations is very important, because you can imagine if you're trying to bind things by charge interaction, if the ionic strength of your solution increases, so everybody knows ionic strength just means you have more ions present, right? They can have a screening effect. So you might have positive, negative charge, but they're screened by the fact that you have lots of sodium chloride or something else present. So then electrostatic interactions become less effective, right? Because you have this screening. So typically, if you are using cation exchange or anion exchange, the lower the ionic strength, the better, because then you don't have charges that can come in between the things you're trying to bind and shield it. That's one problem. The other problem, though, is that proteins tend to be destabilized if they are in very low ionic strength buffers. They tend to aggregate. So it's a trade-off here, okay? But ionic strength and buffer components, therefore, are very, very important in this. And then finally, synthetic polymeric depth filters, spun polypropylene fibers with braided fiber size, used as guard filters on chromatography columns. And we saw that earlier. Some of these sterilizing grade filters may actually be depth filters. And I think for those of you that run chromatography in the lab, HPLC, things like this, you have a guard column, right? And you use that again to protect your column. Same sort of idea here. Okay, now what I'd like to do is talk about tangential flow or cross-flow filtration. And so this moves into a second part of this whole work. So just remember, depth filters can be standalone or they can be used after centrifugation. Tangential flow microfiltration actually is very similar to reverse osmosis. So in reverse osmosis, what happens, you have something like this. You have a feed stream that's flowing through a channel which contains a membrane. You apply a pressure perpendicular to the whole thing, so you remove your permeate, right? And you can use this using flat sheets. You can use it using tubular membranes. You can use hollow fibers. I think everyone is familiar with these configurations or not? Yes? Yes? Okay, good. So actually, the idea of tangential flow, also sometimes called cross-flow microfiltration, came from reverse osmosis. This was developed first for reverse osmosis, and then later people figured out that actually you could use it for ultrafiltration and microfiltration as well. So it's a more recent development. So here's a typical case. Here's your bioreactor. You want to clarify it. So you run your feed through this device. The retentate goes back, and you keep removing your permeate. It's very nice. Now, what are some of the disadvantages of this? Well, compared to depth filtration, the amount of permeate you remove per pass is very low, right? You've got to run this many, many times before you remove what you want. However, compared to depth filtration, the good thing is that you won't get so much clogging, because most of this particulate matter, you hope, will pass through and just keep going around and get concentrated because you're using the cross flow or the shear forces acting due to pumping through the channel to move away or to sweep away the particulate matter. So the cake layer growth is suppressed, right? That's the whole idea of tangential flow microfiltration. Actually, it's a very nice process. As I've said here, microfiltration competes with centrifugation, depth filtration, expanded bed chromatography for initial harvest of therapeutic proteins from mammalian, yeast, and bacterial cell cultures. Expanded bed chromatography, by the way, is also known as fluidized bed for chemical engineers. But in the biotech industry, it's called expanded bed chromatography. That's just a marketing idea. So the point here is that this works very well, and you would think it is a great idea. The problem is this: it was very popular in the 90s, and then it kind of lost popularity after that. And the reason is our cell titers increased. So we became better at growing cells at very high density. We like to do that because if we can grow cells at higher density, we produce more product, right? So your product titer goes up. The problem with that is you end up with more cell debris when you start to do the clarification step, and these filters tend to foul. And so that's why tangential flow microfiltration kind of has decreased. Its use decreased a lot in the 90s because due to fouling and things, it was easier to use centrifugation and put a depth filter at the end of it. But this is still a nice process. It's nice for another reason. It can be made continuous very easily, and people like to move towards continuous biomanufacturing. So there is a revival today in trying to see how to make tangential flow microfiltration work. Oops, what happened? Your PC is, it's not on my PC, it's somewhere here, somewhere else. Okay, well, we can talk a bit while that comes back. So today there's a great deal of interest because tangential flow microfiltration, like reverse osmosis or other ones you use in water treatment, can be made continuous very easily. Depth filtration, we talked about it yesterday. You could, but you've got to have parallel rows of depth filters. You've got to know when to switch on and off. That's just more tricky. So let me now continue with this and explain to you what a couple of things. One comes from some of the research that we do on a novel configuration for depth filtration, for tangential flow microfiltration. And then I think maybe tomorrow or Thursday, I will talk about something called alternating tangential flow microfiltration, which is a new way of operating this developed by a company called Repligen that is used with a perfusion bioreactor. So while we're waiting for that to come up, yesterday we talked about fed batch, right? So everyone knows what fed batch is, or maybe not. So you have a bioreactor, okay, it's a batch process, you've got nutrients there. Every so often you add more nutrients because they're starting to get depleted. You take out a little bit of the liquid, the growth medium, which has got waste products, and it's called fed. So it's a semi-batch process. And then at some point you stop, you harvest it, and you recover your protein, and you do your clarification step. Perfusion bioreactors are different. What you'd like to do is you have your bioreactor here, you're continuously adding growth medium and nutrients, you're continuously removing your product. Now, this is actually quite complex because you've got to ensure sterility. If for any reason it's not sterile and you're adding stuff and taking out stuff, that becomes very complicated. Your cells could get infected, and mammalian cells are very tricky because they're very slow growing compared to, say, microorganisms and E. coli and things like this. So it's very easily outcompeted and they'll die. So that's a big problem, okay? So perfusion bioreactors are very common today, but finding ways to continuously remove the product is difficult. And that's where alternating tangential flow filtration comes. Are we right now? Can I keep going? Okay. So, thank you. So this is the idea now of tangential flow microfiltration, okay? Why? Okay. So I'd like to just highlight the following. So if we look at normal flow and tangential flow, in normal flow, the cake layer buildup leads to eventual termination of the permeate flow, right? It has to stop because you're going forever. Tangential flow of the feed suppresses cake layer buildup. So that's an advantage. I say cannot regenerate the membrane. I suppose in the lab you could do it, but in practice it's not possible. The whole idea of tangential flow is you reuse the membrane. So if you are setting up a tangential flow filtration system, the idea is at some point you will stop, you'll what they call clean in place and run it again, okay? So the membrane is cleaned in, sorry, there's a spelling error here, place and reused. Bioreactor harvesting, this is done also for ultrafiltration. Normal flow filtration, lower capital cost. Tangential flow needs an extra pump, right? Because you've got to pump the retentate around, so it's more expensive immediately. Because a pump means more control systems and all sorts of things, so it is more expensive. In normal flow, you maximize the concentration of rejected species. In tangential flow, you always end up with a retentate that has quite a lot of your liquid there, right? That's a problem, because remember, your product is floating around there, so you've got to find ways to recover that. Normal flow is actually very good for screening membranes. If you're trying to design a system and you get membranes from Millipore, Paul, everybody, you can do normal flow filtrations. You've got a very controlled system, test all the membranes very quickly, find out what looks good, then run tangential flow. Tangential flow is much more time consuming if you want to test multiple membranes. And it's difficult because you've got to control 3 pressures and so forth. So simple operation versus more complex operation for tangential flow. So those are the main differences, okay? Now, as I said here, centrifugation and depth filtration preferred over tangential flow filtration, even though tangential flow filtration has all of these many advantages. And I explained why we were waiting, why that was the case. But there is growing interest in continuous biomanufacturing, and continuous cell culture will require the development of continuous downstream processing. And the major bottleneck today is continuous downstream processing operations. Everything we talk about, chromatography, packed beds, these are all batch processes, right? So you've got to make them continuous somehow. Use of an external tangential flow filtration unit is ideal, since by using an appropriate membrane pore size, a cell-free permeate may be recovered that can be directly introduced in the subsequent capture steps. Remember, centrifugation, you need to put another depth filter in there, okay? But with tangential flow microfiltration, if you use the right pore size, you can take that straight into the chromatography column. That's a big advantage. TFF-based processes typically use 0.2 micron pore size. As cell densities, I told us, have increased, increase in cell debris have caused high levels of fouling and lower product recovery, which has limited the use of TFF. TFF and ATF theory will be presented in ultrafiltration lecture 5. I'll come to that in the next lecture. So let's talk about some work that we had done, which is a way to try and combine a depth filter with tangential flow filtration, okay? So here's a schematic that my student did actually, where you have centrifugation and then some sort of depth filter, flocculation, a depth filter, or you can just have a depth filter by itself. These are some of the methods we talked about. So cell clarification involves multiple operations. We've discussed this. Understanding membrane structure and filtration performance is important because that is limiting. And so what I want to talk about is a fouling mechanism, something called a biooptimal MFSL microfilter. This is made by Asahi Kasei, okay? It's their basically tangential flow microfiltration filter. But it's interesting. So here's a schematic representation of the filter. It's a hollow fiber, okay? So Asahi only makes hollow fibers. So they are like this, and basically you have a feed port, so the feed comes in here, the retentate comes in here. There are 2 permeate ports, but typically only one is open, you remove the permeate, okay? So this is a very standard hollow fiber module. What's different is this: if you look at the membrane, the feed actually flows along the support structure. This is the barrier layer. So it's an asymmetric membrane, but the feed is in contact with the support structure. So what does that mean? And actually the particle size, the size here, this is about quite big. This is about 40 micron on this side. On this side, it's 0.4 micron. Okay, so it's a big change in pore size. Now, typical mammalian cells, how large are they? 10, 20 microns, something like this, okay? So they are going to actually go into these pores. They're not going to be on the surface. So the whole idea is that the cells will go and get trapped in the pores. So it acts like a depth filter initially. And then after that, it acts like a tangential flow system. Now, there are fouling components in these filters. Actually, we've done a study on this. So if you're interested from a research perspective, we could talk about that. What sort of host cell proteins, what sort of DNA fragments actually lead to most fouling. And at the moment, this research project we're doing is using artificial intelligence methods to try and identify what they are from different cell cultures. So that's something we could talk about if you like as well. But the point is that they foul the membrane. So the idea, the hypothesis is that if you have the cells here, they form what's called a dynamic membrane, right? They're forming a secondary layer, and these fouling species will adsorb onto the cells, not foul the membrane. So you should get much higher productivity because you're not blocking pores. Think of your blocking models. You're actually not blocking pores. The pores are somewhat closed because you've got these stabilized cells, and then you're adsorbing onto the cells. So that's the whole idea of this, okay? So that's how this works. And so here's just another schematic representation whereas in a typical microfiltration system, you have the tight barrier layer facing the feed, and so everything is stopped there. But then you can still get fouling by these other species that absorb onto the pores. So this you try to stop it by running in this direction. So this idea, what's called reverse asymmetric structure, it's a reverse asymmetry because the more open side faces the feed, actually was proposed a long time ago, at least 20 years or more ago. Some of the early microfiltration data suggests that for yeast filtration, this actually works quite well, and you can get better capacities from microfiltration membranes, okay? Now, I should say that yeast filtration, people talk about as a model. You have to be careful. Yeast are very rigid cells. Mammalian cells are very, very delicate and flexible, so they'll break easily and they'll deform. So their properties are quite different, okay? So that's something to be careful about. So I'm going to talk a little bit about this work. I'm going to talk about the modeling we did. So I'm hoping for those of you who are engineers that will be interesting. And for those of you who are not, I'm going to try and explain it in qualitative terms. Okay, so we'll see how we go. So it's given reverse asymmetry of a membrane. At the commencement of microfiltration, the filter will behave like a depth filter, right? Where cells will be captured by the membrane. The internal cake layer will be stabilized by the membrane. And then all of you should know this, the transmembrane pressure drop is just going to be the pressure of the feed plus the pressure of the retentate divided by 2, the average pressure on the feed side minus the permeate side pressure, right? That's the tangential, that's the transmembrane pressure drop. You do that in reverse osmosis in all sorts of processes, right? So that's fairly straightforward. Assuming laminar flow inside the tube, you'll have an expression like this for the wall shear rate. So laminar flow just is a type of flow, okay? We tend to look at flow regimes, as we call it, in fluid mechanics, and laminar flow is a certain type of flow that occurs at lower flow rates. The wall shear rate you could think of is that if I'm running flow across this, there's going to be some sort of shear stress that tries to pull this whole table along, right? And a measure of that is the wall shear rate. That turns out to be quite an important property in fluid mechanics, okay? But that's what that is. And this equation that comes up here, I think some of you will be familiar with this. This is just the wall shear rate when you have laminar flow, assuming Hagen-Poiseuille equation, okay? All right. So this is the way we ran this. We wanted to try and see, can we come up with a model to explain the behavior of this membrane? And so what we did is we can set it up where we run it in normal flow mode. So we can run this in normal flow mode. What we do here is the feed is coming this way. So typically we run our feed in dead-end filtration by using a nitrogen tank to pressurize the feed, right? That's our driving force. Comes through here, and then it comes through the filter, and instead of having retentate coming back, we just close the retentate line. So it's forced through the pores, right? So that's a normal flow mode. So we can do that. And if we did it that way, we can determine things like the membrane resistance and so forth. That shouldn't change, right? Shouldn't depend on the flow regime. And then we can also run it in tangential flow mode, as you can see here. But what we can do is we can do something interesting. We can put a valve here. So we can artificially change the resistance through this loop, right? If I put a valve here, I'm putting a restriction here, so there's going to be a greater resistance to flow in this loop, right? So if you remember things like Ohm's law or other sorts of flow processes, but even I think just qualitatively, if the fluid comes here, it has a choice. It can continue along this loop, or it can go through the membrane pores, right? And actually, the way it happens that one works out how much fluid goes one way or the other is that the actually resistances that have to be matched, okay? So the amount of flow that goes that way relative this way just depends on the relative resistances, okay? It's like in electric circuits, right? You have two resistances and you have a bifurcation, and so the amount of current that flows one way or the other will depend on the resistances. So all we are doing then is artificially changing the resistance through this way so we can flow more this way, okay? That's what we're doing. That was the purpose of these experiments, okay? All right. Typically, tangential flow filtration for bioreactor harvesting is run under constant flux. And I have said why. Does anybody have any idea why? So reverse osmosis is constant pressure, right? Right? Typically constant pressure. But forget about this biooptimal, just in general, bioreactor harvesting is run under constant flux. Does anybody have any idea why? Yeah, yes, you can do it that way. Yes, I agree. But why do you want to do constant flux instead of constant pressure? So the reason is this. It's a more difficult question. The reason is this. When you start microfiltration, okay, remember microfiltration membranes are very porous. They've got very high permeability when they're clean, right? You will have very high fluxes if you're running under constant pressure. You'll have very high fluxes. And these very high fluxes will mean that cells will be brought to the membrane surface very quickly. They'll be smashed, they'll lyse, and they'll foul the membrane. If you run at a constant flux, you're controlling that, you see. So the aim is to try and prevent cells from going and smashing against the membrane and lysing. So typically, people run it under constant flux, okay? Now, when you use a reverse asymmetric membrane, that's not true, by the way, for ultrafiltration, okay? That's a different story. Now, when you use a reverse asymmetric membrane, I told you we want to stabilize cells in the membrane structure, right? This is a depth filter. We actually don't want the cells to go and get smashed there. So eventually, what we end up doing is running at very, very low pressures. We want very low pressure drops. That's one thing about this process. If the pressure drop is high, you're in trouble. And so it tends to be run actually at very, very low pressures. And it tends to be more constant pressure, but a very low pressure. Okay? So that's one difference about this. If you run it in the traditional way at constant flux, you'll probably not be very successful. Okay? Then I said here, so the thing about this is that you only control the feed flow rate. The operation is easier. In our work, we do set an initial TMP. So this is what I was explaining here. The feed flow comes here. We have a valve on the retentate side. And on the other side, the resistance of the cake resistance and the membrane resistance, right? And the resistance must be the same for both flow paths. And that will determine how much flow goes one way or the other, okay? So feed entering our hollow fiber has two flow paths, through the fiber lumen and exit via the retentate outlet, or through the membrane and exit via the permeate outlet. Pressure drop for flow through both paths must be the same, and this determines the relative amount of retentate and permeate flows. The resistance to retentate flow may be modeled by the valve and the retentate line. The resistance to permeate flow may be modeled by the cake resistance and the membrane resistance, okay? So CHO cells are highly compressible, so we need a correlation between the resistance of the deposited cells and the TMP. So you know the resistance will change. If you have a higher pressure drop, the CHO cells will squash. And as they squash, the porosity decreases. So that's a problem. Yeast doesn't do that, okay? Yeast are rigid, they have a cell wall. So we need a correlation. We need to be able to relate how much the cells squash as you apply a pressure. This may be obtained by normal flow filtration. I showed you how we do our normal flow filtration using a combined pore blockage and cake filtration model developed by Ho and Zidney. If you are interested, I can give you this reference. I didn't put it here because I didn't want to make it too complicated. But remember we talked about those blocking models? So these people, Andrew Zidney at Penn State, basically came up with a thing where he links two of them, pore blocking and cake filtration. And that's the model we're going to use, okay? The model assumes initial pore blockage followed by formation of a surface cake layer, exactly what happens in this membrane. Model is based on classical fouling models. We talked about them. Permeate flux and cake resistance are given by the following equation. So I don't want to bore too many of you with this, but basically this is telling the flux. And it's given, and you can see there are two terms here. There is this term that corresponds to the cake resistance. This is more like classical pore blocking work. And you can see that actually there's an alpha that actually is a compressibility factor, and you keep integrated with time because the cake resistance changes with time, right? Because the more stuff that gets stuck there, the worse it gets. And then there's this other exponential term here that's here as well, because you've got two terms. You've got a surface filtration term and a cake blocking term. And the overall cake resistance given by all this, okay? If you are interested, we can talk later, and also we can look at the papers, okay? But it's actually all derivable from classical things. And the next slide is just to give you what all the variables are. But I won't go through that now. I think they're going to have the slides, right? So they can look at it if they want. So from a qualitative perspective, you see what's happened is we're taking a blocking model for plugging of pores, and we're taking a model for surface filtration, and we're putting them together. And so it is assumed that the cells and cell debris are completely rejected by the tight barrier layer. And there are three parameters that we actually have to get from that. If you went through the mathematics, something called alpha, which is the resistance of a single cell, RC naught, which is a cake resistance, and then the specific cake layer resistance, alpha prime. So all I'm trying to say is that when you come up with these models, you like to have a model where you don't have a lot of variables that you have to just fit, And we need 3 of these. And we can actually determine these 3 by doing some of those normal filtration experiments and tangential flow filtration I showed you earlier. Okay? So by doing all that, we can then substitute in here. I'm going to skip this for the moment. Oh, one thing I want to point out here. Typically, I was talking about a membrane resistance and a cake resistance. Sometimes people put this extra one in, which we're not talking about. We don't include it. It's a resistance due to something called concentration polarization. Does anybody know what concentration polarization is in membrane processes? Yes. Yes. Yes, and that leads to a resistance, right, to flow. And it also, in the case of reverse osmosis, can increase your osmotic back pressure and various things like this, right? So that is a concern, but in microfiltration, it's not really so important, so we don't talk about it here, okay? All right, so, so this is some more mathematics where we can combine all this, and you can read about this. I just wasn't sure how many people would be from engineering and how many from other backgrounds. But what I wanted to show you is here. So then we did a lot of experiments where we look at the effect of the concentration of CHO cells versus time. And the circles are the experimental data, and the curves are our model predictions, okay? So we ran experiments, we determined those 3 parameters. Based on those parameters, we then run other experiments and try to fit the model. And the model fits quite well. What you see here, though, is this is 2 million cells per ml, 1 million cells per ml, 0.5 million cells per ml. So these are important parameters. These are in the range that people use in the biotech industry, okay? And you can see the effect of TMP on CHO cell filtration as well, okay? So you've got a flux and time, and these are different TMPs, but look, they're all very low. So 1 psi is like 1/15th of an atmosphere, okay? So about 15 psi to an atmosphere. So it's about 1, so it's very low pressures, okay? And then this is some more fits that we're doing, plotting the variation of. Yes, TMP. It has to be very low. It has to be very low. Otherwise, you'll get smashing of the cells. But the nice thing is that actually it's a very porous membrane, so the fluxes are very high, and they've got very high capacity, which means you can run a lot of feed through it. But yes, the pressure is very low.
So it was not under gravity as well. It was much lower than that.
Yeah. This is it's not. No, we are controlling it. I suppose you could do it under gravity, but we didn't. No. And in the biotech industry, you probably wouldn't because it's just not so controlled. But yeah, you could do that. You could do that. So, so these are some more comparisons. Now, what I wanted to show you here is, and this is all in a publication that we have. This is looking at flux versus throughput. So throughput is the amount you can process in liters per meter squared of membrane surface area. And what's really telling is this. This is the biooptimal filter that you can see here at 2 different fluxes, LMH of this and this, okay? 2 different starting values. But see these 2 that end here, this is something called UMP. So UMP is a traditional microfiltration membrane where the barrier layer faces the feed. And you can see very soon the throughput goes to 0. So you cannot continue because there's too much fouling. That's the point here. And then this is another one that's showing flux versus throughput for different cell concentrations. You can see as the cell concentration goes up, of course, the flux is going down. And then again, biooptimal versus some of these that collapse immediately. And those are going to be more traditional membranes where the barrier layer faces the feed stream. Okay, finally, one thing we did that was quite interesting. So we wanted to see where exactly is stuff adsorbing, okay? And so what we're doing here is looking at confocal microscopy images. And so this one is just going to be DNA, and then this one is going to be host cell proteins. And where they come together, where you get pink, that's most likely cells, because cells will have proteins and DNA, okay? And so you can see where they are adsorbing, and you can see that you get stuff all through the membrane, but also particularly here on the inner area, okay? And if you look at here what happens, so this is the biooptimal, okay? This is the one that has this reverse asymmetric structure. But these are traditional microfiltration membranes where the barrier layer faces the feed. So there's nothing in the membrane. It's all on the surface. But here you can see this really is acting as a depth filter. You're getting significant adsorption inside the membrane. And that's what allows you to actually have the much higher fluxes, okay? And the much higher capacity. So this is a very interesting membrane. It's made by Asahi, and we did quite a lot of work on that. And it's one that actually could be quite interesting for continuous biomanufacturing. Okay. So I just wanted to mention one more thing. If we consider the future of this sort of tangential flow filtration for bioreactor harvesting, one idea is going to be this alternating tangential flow filtration, which is something we'll talk about on Thursday. But the idea is that basically in tangential flow filtration, like here, what happens is you have your feed coming out like this. It goes through the module, the retentate is pumped back in, right? So it's just going in a circle, right? The cells come and go. In alternating tangential flow, it's slightly different. See, what happens is you take the feed, it comes out here, it comes into this diaphragm pump, and then you pressurize the other way, so the feed is pushed back in. So it's going backwards and forwards, and each time it makes a pass, you're removing some permeate, okay? By reversing the direction of feed flow, you significantly reduce fouling. All right, because you're breaking up concentration polarization, you're going backwards and forwards, and it's shown that this can actually run for days without significant fouling. The other thing is that you're preventing cells from running around an external circuit like this, and you don't really want to do that because you put stress on the cells. If you don't lyse them, they may not grow so well, they just are not so happy. So this way you tend to try and reduce cell damage as well. But that's something we'll talk about later, but that's where some of this work is heading, okay? So that's the end of that. We have about 10 minutes. Shall I start? Oh, questions firstly. Any questions?
What kind of pump should we use there in the alternating tangential?
Peristaltic, typically peristaltic, typically. Yeah.
So you don't get any pressure?
What do you mean?
You don't get a driving, you don't get a delta P, I mean very low transfer rate.
When you're using peristaltic, yes. Peristaltic pumps cannot have a high pressure, yes. And you don't want a high pressure typically because, as I said, they like to run at constant flux. And also with mammalian cells, you tend to lyse them, you don't want to do that. So it's typically low pressure operation. Yeah. Okay. So we have a few minutes. Maybe I'll just start to introduce the next one. Then we'll stop and take a break, and then we can do something after that, right? So the next topic, I think, was sterile filtration. Am I right? Lecture 3, lecture 4 is sterile filtration, yes. Now, if I just go to this, can the do I need to stop sharing? And I need to stop sharing and redo it, okay. So, it's connecting, right? Is it connecting or do I allow?
Yes.
Okay, good. All right. So maybe this is a good way to introduce this. So we've talked about microfiltration, right? But sterile filtration is also a microfiltration process, right? Because I told you using 0.2 and 0.45 micron membranes. Sterile filtration is always run in dead end mode. Okay, always. You never run it any other way. And it occurs everywhere, okay? Most biotherapeutics are processed by sterile filtration since thermal stability of these molecules prohibits use of alternative methods, right? Other ways to get rid of microorganisms, you can do gamma irradiation, you can do autoclaving, you can do all these things. Your protein is going to be destroyed, okay? So that's why sterile filtration is important. Sterile filters operate in normal flow mode with bacteria cell, debris, and insoluble aggregates retained by the membrane. Filters are used to remove bacteria particles from feedstock solutions to protect downstream units from fouling by insoluble materials and for sterile fill operations. Capacity of the filter determined by fouling characteristics of the feed solution. Fouling can occur on the upper surface of the membrane, both by pore blockage and by cake formation or deposition within the membrane pore structure. Fouling causes a decay in flow rate for constant pressure operation, and it increases pressure during constant flux operation. Remember two things. You're trying to show that you're removing microorganisms, right? But in reality, there are probably not many microorganisms present. You need to be able to validate that. But what's very important is that you remove product aggregates and product variants that may actually cause problems later on and are things you don't want anyway in your drug, okay? All right, so a summary of this. Flux decline data typically analyzed using one of the classical filtration models. So everybody knows what these are now, right? Pore blockage, intermediate blockage, pore constriction, cake filtration. Everybody knows what these mean, I hope. And you can do it under constant pressure or constant flux. Okay, same models. It works very well actually for sterile filtration. This is a case where it works very well. But remember, sterile filters are also not track-etched membranes. They are also going to be typically phase inversion or something else, so that you have a lot of interpore connectivity, because that maximizes capacity. What's important here is capacity. Capacity means how much you can process before your flux is too low and you have to abandon it. Okay. Another thing to remember, in batch processing, the last thing you want is to have to, I mean, you cannot change a filter during a batch. You cannot. It's not sterile, right? It's impossible. So you have to size your equipment so that you can process the whole batch, because if you don't, you're going to lose the batch, and that could be millions and millions of dollars. That's huge. Okay. So often these are designed with a lot of redundancies, but capacity is very, very important. Okay. Now, a few things here, and I think then we'll take a break. So results are expressed in terms of filtration time and cumulative filtrate volume. So how much can you filter in a given time? Linearized forms convenient for data analysis and model identification are used. In each case, the rate of fouling is assumed to be proportional to the rate at which foulant material is brought to the membrane by filtrate flow. In other words, the amount of fouling is proportional to the amount you process, right? Because it's dead-end filtration. So filtrate flow means everything that comes to the membrane surface. Okay? Neglecting any back transport or detachment mechanism. So you don't assume anything can detach or go backwards. Okay. For cake filtration model, fouling results in a deposit on the external surface of the membrane that provides an additional resistance to flow in series with that of the membrane. So that's on the surface, cake filtration. In the other three models, what was that? Intermediate blocking, complete blocking, right, and so forth. Membrane is assumed to be composed of a parallel array of cylindrical pores with uniform pore size. The pore constriction model, fouling occurs within the membrane pores, leading to reduction in effective pore size. Standard intermediate blocking, the pore blockage models assume pores are occluded by foulant, with intermediate blocking allowing for particle superposition on the external membrane surface. So intermediate just means that you don't block the complete pore. Okay. Many investigators have used simple fouling models to analyze flux decline data. Considerable experimental evidence exists for transition in fouling behavior from perhaps initially the decline associated with pore constriction and or pore blockage to finally cake filtration. That makes sense, right? So initially you're blocking inside the pores, and then finally you're starting to block outside the pores. Ho and Zidney developed a combined blockage, model that I talked about. I didn't go into all the mathematics, but they derived their model specifically for sterile filtration. We applied it to that Asahi model, okay, Asahi module membrane, and that accounts for this transition. Protein aggregates and cell debris assumed to deposit on the membrane surface, blocking the pores, but initial deposit assumed to be at least partially permeable to flow. That's part of Zidney's assumption. Cake layer or deposit begins to form over regions of membrane that have been blocked by the initial deposit. So you've got your membrane, it's not uniform, you get various parts of the membrane where you get blocking inside, but where you get blocking inside, then you start to get cake formation. Okay. The model more successfully describes fouling of protein aggregates than classical filtration models. Why? Because you have lateral permeability, you don't really have straight through pores, so this model is actually much better. Okay. Okay, a framework underlying combined pore blockage and cake filtration has been extended to account for the effects of complex pore morphology in current sterile filtration operations. You've got asymmetric structure, pore interconnectivity, lateral permeability. Interconnected pore structure allows the fluid to pass around a blockage and therefore significantly reduces flux decline, as I have said already. So I think that is a good place to stop. We'll pick this up then at that point after a tea break, right? How long do we stop for? 15 minutes, okay. And at that point, we'll start again and continue from there. Okay? Should I just leave it on or? Yes. Okay.